In this video, we are going to do an optimization problem. A cylindrical can is made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So, in order to minimize the cost of the metal to manufacture the can, we need to minimize the total surface area of the cylinder. So let's start by drawing out our cylinder. So we don't know what the dimensions of the cylinder are, that's what we need to find. So let's suppose it has radius r. We'll suppose that the height is h. So what is the surface area of this cylinder? Well, what's the area of the top and bottom? The top and bottom are just 2 circles. So what's the area of a circle? It's pi r squared. So this base has area pi r squared. And up here, the top part also has area pi r squared. Now, what is the area of the part that wraps around the cylinder? Well, it's basically a rectangle that wraps around. So that part is going to have length, the circumference of a circle. So that's going to be 2 pi r. And so it's going to open up to be a rectangle that has length 2 pi r and height h, right? Because what happens to this, it's going to wrap around to form a cylinder, right? So you can kind of envision this. Yeah, okay. So now let's put this all together. So what's the area going to be? It's going to be the top and the bottom circle. So 2 times pi r squared plus 2 pi r h. Great, so we have an equation for the surface area of the cylinder, but we have it in terms of 2 variables, the radius and the height. We want this equation to be in terms of 1 variable, the radius. So let's try to find a way to express the height in terms of the radius. What other information are we given about this? We're given that the cylinder can is made to hold 1 liter of oil. So note that 1 liter is equal to 1,000 centimeters cubed. Now, if the can hold this much oil, what are we measuring? We're measuring volume. So what is the volume of a cylinder? The volume of a cylinder is pi r squared height. And we know that this is equal to 1,000 centimeters cubed. Great, now we can solve for h by dividing 1,000 by pi r squared. Now we can substitute this value for h. So what do we get? We get that the surface area is 2 pi r squared plus 2 pi r 1,000 over pi r squared. So we're going to have some cancellation here. This is 2 pi r squared plus 2,000 over r. Great. So we have this function of the area in terms of the radius. Now, what values can r take? Well, it definitely has to be positive, so r is greater than 0, and r can be as large as possible. So there's no maximum value. R is not bounded by anything. We just know that it's positive. So the next thing I'm going to want to do is take the derivative of this function and set it equal to 0. So first I'm going to rewrite a of r as 2 pi r squared plus 2,000 times r to the minus 1. That way it's a bit easier to take the derivative because we can just use the power rule. So what is the derivative of this with respect to r? So it'll be 2 pi times the derivative of r squared, which is 2r, plus 2,000 times the derivative of r to the minus 1, which is minus 1 r to the minus 2. So let's simplify this a bit. This is 4 pi r minus 2000 over r squared. Now we want to set this equal to 0 and see what values of r make this 0. So I'm going to rewrite this as 4 pi r cubed minus 2000 over r squared. And I can factor out a 4 from the numerator. So this becomes pi r cubed minus 500. Oops. All over r squared. So we know that r can't be 0. R is strictly greater than 0. So when does this equal 0? Well, it equals 0 when this part equals 0. So when pi r cubed minus 500 equals 0. So I can add 500 to both sides. Then I can divide by pi. And now I can take the cube root of both sides and get that pi equals the cube root of 500 over pi. Now what does this tell me? This is a critical value or a critical number. And so what we want to do is see where our function a is increasing and decreasing, and we want to see if this critical number is a maximum or a minimum. So we can plot this. And we know that r is bounded below by 0, so you can choose some value between 0 and this number, let's say 1, and if you plug that into the derivative, 4 times pi r cubed minus 500 all over r squared, we see that in this interval here, the derivative is less than 0. Now we can choose a number larger, let's say 100, and if you plug 100 into 4 times pi r cubed minus 500 over r squared, we see that on this interval, a prime of r, the derivative, is greater than 0. So what does that mean? That means that for values less than the cube root of 500 over pi, we have that a is decreasing. For values greater than that, it's increasing. So if we have decreasing and then increasing, that means that this point is a minimum. So what does this tell us? This tells us that this point is an absolute minimum, and so that means that r equals the cube root of 500 over pi is the dimension that gives us a minimum surface area, which means that that will minimize the cost of the metal. But we need the other dimension, which is the height. So recall that the height is equal to 1000 over pi r squared. So that means it's going to be 1000 over pi times the cube root of 500 over pi squared. So the problem asked us for the dimensions that will minimize the cost to manufacture the can, and so that answer is going to be a can with this radius and a can that has this height as well. And so this is the final answer. If this video was helpful, feel free to like and subscribe.